Inverse functions. Two one-to-one functions, f and g, are said to be mutually inverse if these two conditions apply. F of g of x is x for every x in the domain of g, and g of f of x is x for every x in the domain of f. What does this mean? Let's begin explaining what some of these symbols and words mean. First of all, a common notation for the inverse of the function f is f with a -1 exponent. This is a special piece of notation. It does not mean reciprocal. This does not mean 1 over. This means functional inverse. It's a special piece of notation. Now, to find the rule for an inverse function, you can try this. Set x equals f of y and solve for y. What results will be the rule of the inverse function. If you graph the inverse function and the function, they will be the reflections of each other across the line y equals x. Equivalently, if there is a point AB on the graph of f, then the point BA is on the graph of the inverse. In other words, the graph of the inverse contains those points for which the ordinate and abscissa of the graph of f have been reversed. AB here, BA here. Now here's a diagram that might also provide some insight into what's happening here. Let this bottom line represent the number line for a domain of a function f of x. Let this horizontal line be a number line representing the range of that function. So the function f of x takes the number x and produces this number f of x. The inverse function acting on that number returns x. That's the meaning of this statement. If you start with f of x and apply the inverse, you will get back x, which is called the identity function. X goes to itself. X started out here, it took a journey, it came back to itself. By all means, let's try an example to see if we can clarify some of these ideas. Let's begin with a simple linear function. F of x is 2x plus 3, and then we'll explore the graph of the function and its inverse and so forth. So the very first thing we need to do is define this function. Okay, so f has been defined. Now, to get the rule for the inverse, the suggestion is set x equals f of y and solve that equation for y. So this becomes the rule for the inverse g of x, and I will use the notation g of x rather than f inverse because it's easier to type the letter g than it is to create the symbol f inverse. So I want to put this rule to the right of that equal sign, and I'll use this equation label to do that. And I will assign function, and I will show you that the label actually stands for this quantity, x minus 3 all divided by 2. Well, one of the first things we want to do is to verify these two relations f of g of x, that it is indeed x, and g of f of x, that it is indeed x. So if you start out with x and you take a journey through g, f will bring you back, and if you start out your journey along f, g will bring you back. Now, the computation that just took place doesn't show you the algebra or the arithmetic, so let's give that a try. Let's take a look at f of g of x. Well, that's 2 times something plus 3. Okay, so this something would be this expression, the rule for g. So let's see if we can put that between the parentheses and see what the algebra has to be in order for this to come out to be x. So this 2 would come inside the parentheses, and the 2's would cancel. You'd have a negative 3 here, and you would have an x here. And then outside you have the plus 3, so the 3's it is 0, and all that's left is this x. And if you go the other way, if you start out with g, you'd be looking at, let's grab it from here then. You would be looking at this x right here, well, that becomes the rule for f, so that has to be 2x plus 3. So what arithmetic takes place? You have 1/2 of 2x, there's the x, and then you have 3/2 and a negative 3/2, they add to 0, and so that becomes x. Now what about graphical results? Let's see if we can draw some graphs. So I'm going to use a tool that's designed to draw graphs of a function and its reflection across the x-axis. So f of x can go up here. Probably want to move the left endpoint further left, but let's just see what happens. Okay, do a display. Let's try -4. And you begin to see this is the graph of f. This is the line y equals x. And this is the graph of the inverse. And here is the rule for the inverse. Recognize it? -3/2 minus 1/2 x. And these two graphs are the reflections of each other across the line y equals x. That's what we mean about this graphical property. So we have that graph to look at. Now here's another way that we can obtain the graph. Let's use this tool, interactive plotting tool, and I'm going to draw the graph of each function parametrically. So that requires f of x to draw the graph of f. And now I'm going to draw the graph of its inverse by simply reversing the coordinates. I will put f of x, x. That's what I mean about AB and BA being one on one graph and one on the other graph. And then I think I'll add the line y equals x by graphing parametrically x comma x. Okay, so we're going to draw these parametric curves. The parameter x, this is set to run from -3 to 3. We should try -4, and let's limit this to 2. and let's see what that looks like. Now, it looks very much like this graph. This is the graph of f. This is the graph of the inverse. So this is what we got when we did the x, f of x. This is what we get when we do f of x, x. And this is x comma x. Well, here's another example, and this one has a little bit more to it than the case of the linear function. This function is quadratic, and you'll notice that we asked for the inverse of this quadratic function subject to this restriction, x greater than or equal to minus 1. We should draw a graph of f to understand why we have to have that restriction. So let's define the function. And let's draw its graph, and it's easily done by going f of x, hit the enter key. We have the rule. We're going to draw a graph of this function. Well, I don't want to graph it from minus 10 to 10. I will get some pretty big numbers otherwise. I'm going to try minus 5 to 4. Take a look at what that's like. Okay, it's a parabola. The vertex appears to be at minus x equals minus 1. Oh, I might try this at 3, and it has a more symmetric look. But just look at that graph. If you remember the horizontal line test, you draw a horizontal line. We can draw a horizontal line. Let's draw a horizontal line. Okay, we draw a horizontal line. It hits the graph more than once. So this function is not one-to-one. You have an x over here that goes to a y value, and an x over here that goes to that same y value. So there are two x's that go to one y. It's not one-to-one. You cannot invert this function. The restriction, x greater than or equal to minus 1, is basically saying that we really want to look at this piece, the piece from the vertex to the right. That piece is one-to-one. And if we drew that, so if we started at negative 1, we would have a branch that is one-to-one, and it is invertible. Okay, so that's the reason for the restriction. Well, what does that do to our algebra? We're going to try to find the rule for the inverse function, and the process is to set x equals f of y and solve for y. Well, there are two solutions for y. This solution is always negative. This solution is sometimes going to be negative. Mostly it's going to be positive. This looks like the more appropriate rule for our function g of x. So let's give that a try. G of x equals, let's use this rule. A sine function, and test what happens if we have f of g of x. Well, we get this expression. We need to do some algebra on it because now Maple does not immediately simplify it. So let's simplify that. Let's just do a simple simplification. Okay, Maple can expand this parenthesis and we get x. How about g of f of x? Well, now we have something to think about. This expression is a perfect square. And Maple needs to know that that's a perfect square. Take the square root, but there are two square roots. So take the correct square root and do the simplification. Well, let's ask Maple to simplify, assuming that x is greater than 1. And we can do that by assuming a real range. So x, we will tell Maple, lies in the interval -1 and to the right. Under that assumption, Maple says, okay, I can take the square root of x plus 1 squared, and I will get x plus 1. The plus 1 will cancel with the minus 1, and all that will be left is x. Let's look at the relationship of the graph of f to the graph of g more carefully. So we'll make use of one of Maple's tools here. And we want to put in the function f of x, but we only want this graph to run from -1 to the right. Let's see what happens if we stop at 2. Okay, well, the red curve is the graph of f of x. The blue curve is the graph of the inverse of that branch. These are the reflection of each other across the line y equals x. So a point -1, -4 here is -4, -1 here. Now notice that Maple reports as the inverse both branches, because it doesn't know at the time it's doing the calculation which branch you have in mind. So it gives you both branches, and then you have to pick the correct one. Namely, in this instance, it would be the first. Okay, so there's one version of that graph. And we can also use the plot builder to again do this. Graph parametrically f of x. And graph parametrically f of x. And let's do x for the line y equals x. Now, the parameter is x, so I want it to start at -1, -1, and I don't think it has to go more than 2. Let's see what that graph is going to look like. Very much like this graph, except the line y equals x is not as extended as much, but here's the graph of f, and here's the graph of its inverse, obtained by simply interchanging ordinate and abscissa. That's what happens when we did f of x, x. As a final example, let's take a look at the function sine x. Let's see if we can make some sense out of the problem of obtaining an inverse to the function f of x equals sine x. I'm going to begin by defining the function. And I think I'll draw a graph. So I'll have Maple draw me a graph. Well, sine x is periodic. If we draw a horizontal line on this graph, it's going to intersect the graph many times, more than once. Therefore, sine x as it stands is not one-to-one. It is not invertible. You have to pick a one-to-one section. And it's a nuisance to remember what that section is. So now, with that thought in mind, that defining an inverse to sine x is going to require not only the algebra of finding out what the rule is, but also determining which piece of the sine x function we look at. So I'm going to attempt our process of writing x equals f of y and solving for y. Oh, what's this? There's no formula here. There's just the name of the inverse function. It's called arcsine. In other words, sine x is what's called a transcendental function. It's not a simple polynomial. The recipe for computing the values of sine x is complicated. The formula or the recipe for computing the values of its inverse is equally complicated. This function has been programmed into most computer systems like this. It has the name arcsine, and Maple recognizes this notation, sine minus 1 of x. It recognizes that to mean arcsine. And so all of the trig functions have their inverses in this fashion. Arcsine, arccosine, arctangent. They all mean inverse function. Now, having determined that Maple knows the arcsine function as the inverse of the sine function, let's see if we can get Maple to tell us which piece of the sine function gets inverted. Now, if I start out with the arcsine, which is the inverse function, and invert that, I should get back to the sine function, inverse of the inverse. So the way I'm going to do that is I'm going to bring up this tool called the plot builder. And I'm going to graph the inverse of arcsine x. Now the way you graph an inverse is to reverse the coordinates. So I'll put arc sine of x comma x. Now the default domain is -3 to 3. We do a preview. We get a graph that lives on minus approximately 1.5 to 1.5. This is actually pi over 2, negative pi over 2, and pi over 2. Had we changed these endpoints to -5 to 5, we would still get the same graph living on minus pi over 2 to pi over 2. This is piece of sine x, because the inverse of the inverse is back to sine x, right? This is the piece that defines the principal branch of the sine function, and this is the one-to-one piece that serves to invert the sine function. So we can draw a graph of sine x, its inverse, and y equals x the way we've done so far. Make use of this plot builder and graph parametrically x sine of x. So I need a comma here. And then I will do sine of x, x oh, I didn't put a square bracket here. And finally x comma x. Now the parameter is defaults to -3 to 3. Which is going to give you too much of the sine function. This is not a one-to-one piece of the sine function. So you have to here enter minus pi over 2 to pi over 2. So now you can see in red the piece of the sine function that serves as the principal branch, and its reflection across the line y equals x is the graph of the arcsine function. The tutor that we used should provide us the same insight. Function inverse. Let's put sine x here. And for the endpoints, minus pi over 2 to pi over 2. The graph is correct, and the formula for the inverse is given as arcsine x. And so this is the graph that is produced. Red curve is the principal branch of sine x. The blue curve is the graph of the arcsine function.